ugliest X-ray too, my favorite. How the process works for fluoro. It's pretty easy. Got X-rays, you got a body. It's the what? Image intensifier, which is made up of an input phosphor and a photocathode. Then you have electrons. You've got electrostatic lenses that accelerate those electrons towards the output phosphor. Light picked up by various types of things and displayed. So I guess the types of things you're going to be asked to if you get physics questions on your ASRT and tests in this class is, you know, what are these two surfaces? What is an input phosphor? What does it do? What's the photocathode? What does it do? What's the purpose and function of electrostatic lenses and output phosphor? So you just need to know the basic mechanisms of what's going on. This is the eye. Sensitivity of the eye is greatest in the green part of the color spectrum, which is kind of unfortunate because in modern fluoroscopic systems, what colors do we see? We see shades of gray, everything from white to black and in between. What we lost is in the original direct view screen and the direct view image intensifier. When image intensifiers first came out, you looked at the direct output from the output phosphor, and it was green. It was in shades of green and black. So we lost something when we went to shades of gray. Is there a question?
No.
Thank you. I don't know so much that they test you that much on anatomy of the eye. You should know the basic types of things, you know, optic nerve, rods and cones. What are the rods? What do the rods see and what do the cones see?
Rods at night.
Okay. And cones, yeah. So what's interesting is when you're driving at night, you can notice this because colors don't really look colorful. One of the worst sign colors you can see, and I've seen them out here, it's like blue on black. And it's almost very, very difficult to see what the letters are until you get really, really close. But of course, and this is where the lens, this is if you get some radiation damage, this is where it is. What's interesting is it is discernible to tell if it's radiation caused or not, because in a regular cataract, it's typically in the front of the lens. If it's radiogenic, it starts at the back of the lens. And people think, well, that's kind of weird. Well, it's actually not. It's at the end of the track where it deposits most of its energy. So ophthalmologists can actually look at the inside of a radiologist or technologist's eye, and if there is an issue, can tell if it's radiogenic or if it's just genetics. All right, let's go back to this then. You will be expected to know what the purpose of the electrostatic lenses are. Do you remember at all?
To speed them up and focus.
Yeah. So what you have is you have a lot of different energy transitions. You've got X-rays basically transforming to light in the input phosphor, the light being changed to, in the photocathode, to electrons. Those electrons then are accelerated, focused, and then redisplayed on the output phosphor, which then turns into light again. And each one of these stages has different efficiencies, and I think those are in Lynn's slides. Oh, that's cute. Okay, visual acuity. Visual acuity is the ability of the eye to perceive fine detail. Now, this is one of the things you need when you're evaluating anything that requires sight. X-rays, art, gaming, anything where you need to look at fine details. Trabecular pattern on bone, things like that. But that's visual acuity. You'll be measuring your own visual acuity in one of the labs where we're looking at high contrast resolution. Contrast perception. Contrast is the ability of the eye to detect different brightness levels. This is a major issue. Radiologists, this is what they need to do. I remember working with a chief of radiology who mentored radiology residents, and he told me the story of a young man who was medically brilliant. If you put up an x-ray film and you pointed to something that was wrong, he could tell you immediately what it was, where it came from, what you do for it, everything about it. But he couldn't see a lot of them. So they sent him to have his eyes tested, and it turned out his contrast detectability was poor. He had excellent visual acuity, but his contrast perception was not what it needed to be. He ended up giving up radiology and going into surgery. But yeah, that is one of the big things. That's one of the issues when people start complaining about image quality in fluoro. Your older physicians, they will start complaining about, oh, resolution's really poor. Get the service guy in here. Our contrast stinks. I was at RSNA in early 2000s, and a radiologist who I thought was very brave gave a talk about how he had problems with his fluoro system. And they replaced the x-ray tube. They evaluated filtration. They replaced the image intensifier. They replaced all sorts of stuff. They recalibrated. They did a new generator. He spent almost $200,000 on equipment repairs. And it turned out he needed new glasses. His wife pointed that out to him one night when he couldn't read a menu in a restaurant. She said, well, you need to get your eyes checked. He went in, and all of a sudden, his system looked just fine. He spent $200,000 for nothing. He told that story. And there's a lot of laughter, and he stopped that by saying, look, this is what we do for a living, whether you're a physician, a technologist, or what. So when things start going haywire, you can blame the equipment, but make sure you look to yourself first. I've worked with techs that had issues with that. Integration time. Integration time is the time that it takes your brain to register what your eye sees. So everything in your life that you're seeing right now is in 0.2 of a second frames, if you will. Okay. If it goes slower than that, then things appear slow to you, or artificially slow. Anybody watched a Western? You notice the wheels on the stagecoach? Wheels on the stagecoach, they go backwards, they go backwards. Yeah, that's because the integration time of your eye isn't matching the speed of that wheel. So it appears, even though it's going this way, it appears as if it's going backwards. And it's even worse in a movie where the speed of the stagecoach or the car changes. So it's going the right way, and then it stops, it goes the reverse, then it goes this way. But that's integration time. Okay. It takes that long for your brain to say, ooh, I saw it. You will need to know all of these. Question? Okay, this is your image intensifier in a little bit more detail. Same thing as we said before, input phosphor. What does the input phosphor on an image intensifier tend to be? Cesium iodide. There will be a whole different discussion about digital detectors in a different part of the course. That has a whole different thing. Image intensifiers are going away, which is nice, and we'll talk about why. But again, you've got photons changing to light. Light's picked up by the photocathode and creates electrons, which then these photoelectrons are basically accelerated probably right about 25,000 volts. They focus, and then they strike the output phosphor. And you get light. Now you can, if you look at the geometry of this, you've got a round input, a round output, but we view it on a rectangular display. Usually it's masked off, so it's still round. That is a problem. And of course, you'll notice that the path through the center is a lot shorter than from the edges, and that creates distortion. And we'll talk about the kinds of distortion that we have. So, you have a glass, or modern ones are metal tubes, highly evacuated, so you have a vacuum, metal housing to protect the tube. Input phosphor converts X-ray energy to light. Cesium iodide. So the interesting thing about cesium iodide is its normal crystalline structure is like needles on end. So if you look at it on end, it's these fibrous entity that basically helps channel the light. It's almost like a collimator, and it channels that. So usually it can see about 4 line pairs per millimeter. Cesium iodide is blue. Now the photocathode takes that light energy, converts it to electron energy called photoemission. Anode attracts electrons. Like I said, it's about 25,000 volts. There's some aluminum that absorbs the backflow of electrons, so that it's made of aluminum, kind of keeps electrons from going someplace where they shouldn't. The output phosphor converts electrons to light energy. Typically, they use zinc cadmium sulfide. Notice the loss in resolution. We've gone from 4 line pairs per millimeter to 2 line pairs per millimeter. And we've gone from blue to green. Electrostatic lenses are what accelerates electrons. Okay. How does the II tube increase the brightness of the image? It's called flux gain. You're going to have a worksheet that lets you evaluate this mathematically, easily, but it'll work. So if you take one incident X-ray, input phosphor, one incident X-ray creates about 300 light photons that interact with the photoelectrode. Photoelectrode then takes those 300 light photons and creates about 1,000 photoelectrons and send those off to the output phosphor. That output phosphor then creates about 3,000 light photons. So for one incident X-ray, you get about 3,000 light photons. Start multiplying by the number of incident X-rays, and you can see you get quite a gain in intensification. This is what lowered the dose significantly when it was invented from the direct view screens that they used to have that had output of anywhere from 200, 300, 400 R per minute to something much, much less. Current input for the input surface of an image intensifier in modern systems is something less than 5 R per minute. And since it's all light that comes out, and that's all the radiologist looks at, so there's no direct view, radiation exposure to the viewer is very, very low. So flux gain is the number of light photons, the output, versus the number of input light photons. Minification gain. So brightness gets increased due to the decrease in image size. So if you have a 14-inch image intensifier and all that light's going in, the size of that output phosphor is, in your smaller image intensifiers, it's only about 1 inch. In your larger, like 16-inch image intensifiers, it's usually about a 2-inch output. So now you've got all that light produced in 14 inches down to 2. So you have flux gain, you have minification gain. So it's the input squared over the output squared. Brightness gain. Minification times flux. So you have minification gain, you multiply it by the flux gain. Usually brightness gain turns out to be somewhere between 5,000 and 30,000. As image intensifiers age, brightness decreases, gain decreases by about 10% a year for fairly heavy routine use. At some point, you just kind of burn things out. Kind of like a light bulb, at some point it just kind of gives. It doesn't give where it just stops, but it continually decreases. But in order to maintain the output that you need to see what you're trying to do and get the image quality, that means if the gain is going down because of aging, what do you have to do?
Buy new equipment.
You have to increase the amount of X-ray going in, okay? So conversion factors, the luminescence of the output phosphor in candela over the input exposure rate in MR per second. Candela per meter squared, anywhere from 50 to 300. Modern ones can actually be higher. I've tested them well beyond this. Multi-field tubes. Their eye eyes tend to give you multiple sizes. So in a 9-inch mode, you take the entire input and you're putting it on the output. As soon as you drop a mode to like 6 inches, what happens is you're only looking at the central view. By changing those electrostatic lenses, it pulls that focal point closer to the input. So you're still getting light out here, but you're not looking at it. You're looking at the central part. So it's kind of wasted light. One of the reasons why you can collimate, even if you're in 6-inch mode. There should be an automatic collimating feature when you go to a smaller mode, so it brings those collimators in to avoid this issue. So only the central portion input phosphor is used. So the minification gain is less. You're looking at less input, but the same size output. So the KV or MA has to be increased to compensate, which results in an increase in patient exposure. The focal point is closer to the input. This increases the divergent beam at the output phosphor, making the image larger. So that's kind of how it works. But here's the important part. KV or MA is increased, which means when you're going to mag mode on an image intensifier system, the patient is getting more exposure. And it can be significant depending on what mode you go down to. If you're using a 14-inch and you suddenly go down to a 6, you've increased the exposure rate to the patient significantly over a smaller area. So, standard mode, and then if you go to, then you change to a smaller mag mode, then you're going to see only a part of the image. Now, mag mode is very useful. You're going to want to use it when you're looking for very small things. Cardiac cath labs typically use 6-inch, maybe 9-inch fields of view. In the direct systems, where it's not an image intensifier, but it's a direct image recorder, it's always 6x6. So that's the view. Image intensifiers are gradually fading. Okay, when operating the image intensifier in the magnified 9-inch mode from the normal 12-inch mode, the patient will receive how many times more radiation? Normal mode squared divided by magnified mode squared. So 12 squared over 9 squared. So 44 or 81 is 1.8 times. So it's just the square of the diameters. But that's significant. 12-inch, 9-inch doesn't sound like very much. Most of your routine IIs are either 12-9-6 or sometimes they're 14-12-10. But it doesn't sound like much of a difference, but it's almost double the patient exposure, just going from 12 to 9. If you go from 12 to 6, that would be what? 144 over 36, which is 4? 36? Yeah. 4 point something? It's a lot. So, but in magnification, what do you get? You're trading patient dose for higher line pairs per millimeter. Better contrast resolution because you have more x-rays but less noise. Higher patient dose. Okay. Just remember, there is an upper limit to this because you can only magnify so much, and you can't go beyond what the inherent magnification, what the inherent line pairs per millimeter at the output of the image intensifier is. You can't go beyond that. Okay. You can magnify something above that, depending on the system. I have seen systems where you can see 4 to 5 line pairs per millimeter for real super high resolution systems that have really high gain. But for the most part, if you can see 2, 2.5 on a good day, maybe 3, that's good. Vignetting. This is one of the issues when you've got a round input and you have, as I said, remember through the central part of the image intensifier is a much shorter distance to the output than it is from the edges. So you lose something. So this falling off in light intensity, in brightness, is called vignetting. Veiling glare is another issue. It occurs when an X-ray photon is not converted to a light photon or an electron at the input screen. So if it's not converted, basically it means it's gone through both of those. It's gone through the input phosphor, it's gone through the photo system, and it just kind of enters the image intensifier as extra stuff, which create, and if it gets to the output, then it's extra noise. kind of lowers the contrast. So the X-ray photon hits the output screen and produces bright light photons. It kind of lowers the contrast. This is a good example of photographic veiling glare. Pincushion distortion. Basically, this is called barrel distortion. Means the image appears to be mapped around all or part of a spherical object. This doesn't happen that often with image intensifiers. The more common distortion is pincushion distortion, and you'll see that in a lab the next to the last night of class. Magnification of the image increases with increasing distance from the optical axis. So you notice these squares, not only do they become weird shaped, they become bigger. You can see that photographically with low end or very poor telephoto lens. And this is an example. Okay. Almost at the end, folks, promise. How'd you all do on your image intensifier review? Did you get all the pieces and parts matched? Yeah, you keep that. Okay, these are your review questions. See what you can do with these.